Good morning, Abstract Algebra. This is your review session for our first exam, which is coming up at the end of the week this week. So what I want to do over the next 40 or so minutes is take a look back at the material that we've talked about so far. So what do we know about abstract algebra up to this point? What are we able to do? What kinds of reasoning do we engage in? How do we write proofs? How do we do the kinds of reasoning that we're prepared to do at this point in the semester? So to that end, I've picked out just a couple of problems that I want to work through, a couple of proofs that I want to write together during today's stream that can hopefully help us to cement the understandings that we have. So here's what I've got kind of on tap for today. The first piece is I want to do a couple of problems that were recommended in the Slack chat from current students. So if you're watching this live and you're one of my students this semester, feel free to jump into the Slack Doctor's Office channel with questions that you have that you'd like to see addressed. But the first two that I want to look at are the question that if in a group we have a unique element of order 2, so elements of order 2 are called involutions, then that element must be in the center of that group. So this is question 13 on the list of preparation problems. So if there's a unique element of order 2, that element belongs to the center. In other words, it must commute with everything. So that's the first step. Also, there's a problem that I think is particularly nice, which says that any group of even order, so if you give me an even number of elements to make a group with, that guarantees that one of those elements will have to have order 2, that we can't make a group with an even number of elements unless at least one of those elements is its own inverse. So that's item number 2. And item number 3 is question number 18. From the preparation list of problems right here, is that if I have an abelian group, then the set of all elements in that group whose order is finite, so the set of all finite order elements in an abelian group, it's called the torsion subset. And this result shows that the torsion subset of a group actually is a subgroup, right? So it's called the torsion subgroup of G. So I'm hoping that we get an opportunity to do justice to all three of these exercises as we go along today. Let me open up my little proof writing apparatus here before we get started. If you're watching and you're one of my students currently this semester, drop any questions or clarifications that you'd like to see in the Slack Doctor's Office channel as we go along. If you're watching this via Twitch today and you're not one of my students this semester, feel free to contribute your questions into the Twitch chat. I'll get a chance to see them and address them either which way. So let's start out with that first problem that says, so make this a proposition. And proposition says, let G be a group. Let me get it off of the question 13 here of the preparation. Let G be a group that has a unique element of order 2. Has a unique element x in G with the order of x equal to 2. Prove then, this is a statement of a proposition, then x belongs to the center of this group. So there is the statement that we're going to try and prove. I'll get it up here on the screen. Let G be a group that has a unique element of order 2, then that element must be in the center of the group. All right, so let's play around a little bit on the back of a napkin with the various definitions that are going to go into this proof. All right, so on the one hand, we have an element x in my group, and the order of x is equal to 2. So just for a moment, remind ourselves what that tells us about x. The fact that x is an element of order 2 means two different things. It means, on the one hand, that x squared is equal to the identity. When I multiply x by itself using the operation of the group, the result is the identity element of the group. So that's one thing that I know about x. And the other is that because the order of x is not equal to 1, that means that x is not itself equal to the identity element. So those are two things that I know for sure are going to be true about x. It's not the identity, but its square is the identity. Okay, we also know that there is no other element in my group has order 2. So those are kind of the two assumptions that I get to work with here. So that's, if we're going for a direct proof, that would be kind of the material that we would use for a direct proof. Let me get one more napkin up here. So now let's play around with the conclusion. The conclusion of this theorem is that x belongs to the center of my group G. So let's unpack that definition. X belongs to the center of G means that x commutes with everything in the group. Right? That's what the center of a group is. It's the set of everything, all the elements that commute with everything in G. So for all y in my group, we would have xy equals yx. So if we're going for a direct proof, this is what we would, this would be our burden of proof. Right? I would need to show, if you hand me a y arbitrarily chosen, I would need to show you why xy must be equal to yx. All right, so I dropped a hint in the statement of this particular problem. And the hint is that maybe the direct proof approach is not going to be as elegant as trying a contradiction proof. So let's follow this hint and see where it takes us. So the hint says, if we're setting up for a contradiction proof, let's assume that the hypothesis is true, that x is the unique element of order 2, but that the conclusion is false, that x does not belong to the center of the group. Then what that would mean is that there exists some element g that doesn't commute with x. So xg is not equal to gx. And we would then try to use that observation to produce an element y that is different from x. And we can do it in this particular way. So let's follow this hint and kind of see where it takes us. So if the order of x is 2, and x does not belong to the center, so an example of an element x like this would be, I don't know, the reflection of the triangle in the dihedral group of the triangle, right? That reflection is order 2, but it doesn't belong to the center of the dihedral group of the triangle. In our contradiction proof, we would then have to show that x is not unique. X is not the only element of order 2. So how would we do that? So following this series of hints over here, we would be showing that, so again, if we're negating this, x does not belong to the center of G, that means that there exists some element little g such that xg is not equal to gx. And if xg is not equal to gx, then when I multiply by the inverse of gx, I get something that's not the identity. And then using shoes and socks, we can simplify that out to xg, x inverse, g inverse, is not equal to the identity. And then when I multiply both sides of this equation by x, I create an element that's not equal to x. Right. Multiplication by an element of a group on both sides of an equation is a one-to-one operation. It's injective. So if two things are unequal and then I multiply them by the same element, those products are going to be unequal as well. And so the key to the construction here is I'm calling this thing, calling it y. Right. So this new element that I make, x times xg, x inverse, g inverse, I call that element y. And what I'd like to show is that y is two things. It's different from x, which is by assumption, but I also want to show now that y has order 2. How am I going to do that? Well, let's simplify this expression that I have here for y, knowing what I know about x. And what I know about x is that x is an element of order 2. So let me make some space on my napkin here. And since x is an element of order 2, that means that x multiplied by itself is going to give me the identity. So in other words, y is equal to xx gx inverse g inverse is actually just equal to g x inverse g inverse. Right? Because those two x's out in the front multiply by one another and cancel, because x squared is equal to the identity. And so this is my y. And again, we've assumed here that y is different from x because this xg was different from this gx. Right? So this y is different from x. But what is y squared? Y squared is gx inverse g inverse times gx inverse g inverse. And by the associative property for groups, I can forget where these parentheses are situated. I can remove them. And when I remove them, I end up getting a g inverse multiplied by a g right next to one another that are just going to cancel. And I'm going to get g x inverse times x inverse. So x inverse times x inverse, that's going to be x to the minus 2 times g inverse. But what is x to the minus 2? Because x was an element of order 2, x to the positive 2 was equal to the identity, but by multiplying both sides by the power x to the minus 2, we find out x to the minus 2 is also equal to the identity. And so this just gives me g times the identity times g inverse, and that gives me the identity. And so what I find out from this is that y squared is equal to the identity. And now the only question that remains is, why is it not true that y is equal to the identity? How do we know that y doesn't have order 1? And for that bit, let me just go back to the top of this napkin. So why is the order of y not equal to 1? Well, let's argue this by contradiction as well. If the order of y were equal to 1, that would mean that y is equal to the identity element. Right? Identity is the only element in a group that has order 1. And so, for that reason, if y were equal to the identity, keeping in mind what y is g x inverse g inverse. If that's equal to the identity, then what could I do? I could multiply by g, let's say, on both sides of this equation. If I multiply by g on the right of both sides, then identity times g is going to give me g. G inverse times g is going to cancel. It's going to be gx inverse is equal to g. But then if I multiply by g inverse on the left, or just use the left cancellation property, I would find out that x inverse is equal to the identity. And taking the inverse of both sides, that would guarantee x is equal to the identity. And that would say that therefore the order of x is equal to 1. But that's not true by contradiction, right? Because the order of x was assumed to be 2. And so that is the napkin version of this proof. Let's take a moment and write this up a little bit more formally. So I think the trickiest part is that we've done actually almost a couple of different contradiction arguments. So we want to make sure that when we write this up, that contradictory structure is clear to the reader, like what is being contradicted and how. So how did we get this whole process started? We decided up front that what we wanted to do was use this contradictory assumption. So we'll signal that to the reader by saying assume by way of contradiction. This is one of the only places where I use the word assume, by the way, is when we're setting up the reader to be surprised later on. Right? We're trying to lead them down this path that we want to then show them is not the right path to be on. Assume by way of contradiction that the order of x is equal to 2, but that x does not belong to the center of G. And an astute reader of this proof might recognize that this isn't really a contradiction argument unless I also assume that x is unique. Since I didn't assume that, that's going to be the thing that I want to deduce. That ends up being my burden of proof. We will show that then x is not unique among elements of order 2 in this group. So that's now my burden of proof and my strategy. So now we need to show that there is another element of this group that is not the same as x, but which has order 2. And so now is when we're going to jump straight down to this line on my, well, we want to somehow get down to this line where y is equal to g x inverse g inverse, because that's the magic sauce. That's my construction that's going to produce for me another element of order 2 in this group. How did we get there? Well, we had to get g from somewhere, and g is going to be a surprise symbol if I don't tell the reader where it comes from. So where did g come from? It came from the assumption that x was not central. So that's where we pick up the thread. Since x does not belong to the center of the group, there exists an element, g in G, such that xg is not equal to gx. So that introduces the reader to where little g comes from. There exists a little g in big G such that xg is not the same as gx. Okay. So now I know what g is. And then we'll use that g, so skipping down here, we're going to define this g, or we're going to define this y in terms of x and g. Then define, and I'm going to put this on a line by itself just to make it clear, y equals y equals g x inverse g inverse. So I'm just going to skip right down to this line on the napkin. So now the reader knows what y is. It's definitely an element of my group because g, x, and g inverse and x inverse are all elements of G, and we have closure, right? But we need to now convince the reader of two things. We need to convince the reader that y is different from x, and we also need to convince the reader that y is an element of order 2. Let's do the latter piece first. So I'm going to write it out here. Y has order 2, colon. So to do this, we'll pick up with this part of the argument from the napkin. Observe that. So now we'll write out these equations. Y squared is equal to gx inverse g inverse times gx inverse times g inverse. And then again, using the associative property, this is gx to the minus 2 g inverse. I'll just put the byline in here by associativity. And then we make the argument that x to the minus 2 is equal to the identity. And the reason for that is that x to the minus 2 is the same as x squared inverse. So I only actually add that line in here just to increase the clarity. So to show you what I'm doing here. We had x to the minus 2, which we argued up here why that was equal to the identity. Let's add in one step just to make it clear to the reader why that's the case. X to the minus 2 is the inverse of x squared by definition of exponents. But then, by our assumption that x has order 2, this is equal to g times e inverse g inverse. And then when I simplify that out, that's just equal to the identity. And the byline there is by assumption that the order of x is equal to 2. So here's where we're at. We've just shown that y squared is equal to the identity, which is one piece of demonstrating that y has order 2. So how do we know that y does not have order 1? So here's the good place for this argument up here. Furthermore, the order of y is not equal to 1, since if it were equal to 1, y equals the identity implies that this line of reasoning up here, right, that I guess I had it and I erased it. But it implied that gx inverse g inverse is equal to the identity, implies that x is the identity. So gx inverse g inverse equals the identity, and hence x is equal to the identity, which is untrue. So this piece of the proof, proving that y has order 2, that piece is now all set. I'll add in a little diamond here to indicate that this subclaim has now been demonstrated. So now we know that y has order 2. Now we need to demonstrate why y is different from x. Y is not equal to x, colon. So here we're going to also sort of argue indirectly. Assume that y equals x. Then by our construction of how we made y in the first place, let's chase down the consequences of that. So y is equal to gx inverse g inverse, and if that's equal to x, then when I multiply on both sides by, let's say, G inverse, or let's say, no, let's multiply by G on the right. So I'll have G x inverse is equal to xg. Wait a minute, this is probably not the way I want to do this piece of the argument. Gx inverse, G inverse, that's where we had here, right? And if that's equal to x, then I can multiply now maybe we should just run this piece of the argument the way that we had it before. So since xg is not equal to gx, we have, by injectivity of multiplication, the fact that multiplication in a group is a one-to-one operation. Now is when we can go back to this logic here from the napkin. Right? So this piece would say that xg times the quantity gx inverse is not equal to the identity. And then xg x inverse g inverse is not equal to the identity. And there we're using the shoes and socks principle. So let's get caught up here. Looks like I've got a bit of a problem with my syntax. Let me just compile this one more time here. I've got some issues. By shoes and socks. There we go. And then I just multiplied both sides of this equation by x. Y equals x g and x inverse g inverse is not equal to x. And then simplifying xx to be the identity, y equals gx inverse g inverse is not equal to x. And that concludes the proof. Thus, y is an element of order 2 distinct from x. So again, pay attention to the overall structure of the argument here. What we showed was that if I have an element of order 2 that doesn't belong to the center of my group, then I can construct another different element of order 2. And so the only way to have only one element of order 2 in a group, a unique element of order 2, is if that element belongs to the center. So here's the proof for that argument. I'm going to pause here for about 15 or 20 seconds. If you're watching this live and you have questions, clarifications on the proof that we just did, now is a good time for that. This is probably the most challenging proof that we're going to look at today. The next two that we're going to look at are a little bit shorter, a little bit sweeter, a little bit closer to, I think, the difficulty level that might show up on an exam, say. So this one was a little bit more involved, but it gave us a good opportunity to use some definitions that we don't get to use very often. So let me take a short 15-second pause, and then we'll come back for those next two proofs. All right, welcome back. We're going to move forward to our next proof here. And the statement of this result is that if you give me a group with an even number of elements, so if G is a group of even order, then there must exist an element of order 2 in G. So I can't make a group with an even number of elements unless I have an element of order 2 in my group. So how are we going to do this proof? So this proof is going to rest on the following observation. Really, it's almost completely rests on this observation. And the observation is that the order of any element, G, is the same as the order of its inverse. So if I'm an element in a group and you are my inverse, then you and I have the same order as one another. And so what that means is that, let me add in another observation, that if I'm making a group, that group has to have an identity element, and this identity element is its own inverse. And it has order 1, as identity element always does. And then it's going to have some elements of order 2. And elements of order 2 are their own inverses as well. And so we can put in elements of order 2 by themselves into a group, because I don't need to accompany it with a different inverse. But I can also have a bunch of other elements that are not equal to their own inverse, and those elements come in pairs. Right? I can't have only a single element of order 3, for example, in a group, because that element needs to have an inverse by the inverse property, and that inverse will also be another element of order 3. So the plausibility argument for how this works is that I know in my group that I'm going to have one element of order 1, because there's a unique identity element in a group. I'm going to have some unknown number of elements of order 2. So I'm just going to call this, let's call this k. Let's suppose I have k elements of order 2 in my group. And then I have a bunch of elements of order 3 plus. Right? The elements of orders 3, 4, 5, 6, and so on and so forth. Right? And I don't know how many elements of those that I have, but I know that they have to come in pairs. And therefore, the number of elements of order 3 and higher that I have is always going to be even. So there's the key observation here, that I always have an even number of elements whose order is 3 or more, because all those elements have to be accompanied by their inverse, and their inverse is something different than themselves. And so at the end of the day, the napkin argument for this proof is if I assume that my group has an even order, an even total number of elements, then that even number of elements has to consist of the sum of the number of elements of order 1, the number of elements of order 2, and the number of elements of order 3 and higher. And if I add these all up, let's say I call this even number here 2j, or something for some integer j, that the total, the order of the group, is going to be equal to 1 plus k plus 2j. But we've assumed that my group has even order. And so let's assume that the order of my group is 2k. What that does is it sets up this equation, 2k equals 1 plus k plus 2j. How can we possibly solve this? Oh, I'm sorry, I'm using k for two different purposes. Let me fix that. Let's call this 2L instead. So the order of the group is 2L. Now, how do we know based on this calculation that my group has to have an element of order 2? Well, suppose that it didn't. Suppose we had no elements of order 2 at all. That would make k equal to 0. If k were equal to 0, then this equation would become 2L equals 1 plus 2j. And maybe you can see the problem with that. Because the left-hand side of this equation is an even integer. The right-hand side of this equation is an odd integer. And so that's not possible. Another way to say that is to subtract the 2j from both sides. 2 times the quantity L minus j is equal to 1. But 1 is not a multiple of 2. So that's the argument. I'm not going to write up the full flourish of the proof in a formal fashion here. But what this does is it kind of gives us actually what turns out to be a pretty useful scaffold for understanding how many elements of certain orders a finite group can have. we know there's always only going to be one element of order 1, the unique identity. And we know that all the elements of order 3 and higher, because they're not equal to their own inverses, they have to come in pairs. For every one element of order 3 or higher that I have, I definitely have another distinct element of that same order, because that element is the inverse of the former. And so it's only elements of order 2 that can be put into the group sort of by themselves, because they're their own inverses. We don't need to put them in pairs. And so for the elements of order 2, if the total order of my group is even, that means that there's no way for me to have 0 elements of order 2. I have to have at least 1. And in fact, we can make an even stronger statement here. Right? If I were to solve this equation for k down here at the bottom, and this is how I'm going to finish up this proof. If I solve this equation for k, I get k is equal to 2 times the quantity L minus j minus 1. And what I learned from that expression on the right-hand side is that that number is odd. So we can actually make a stronger conclusion here. Not only is it the case that there must exist an element of order 2, we can in fact strengthen the conclusion by saying there must exist an odd number of elements of order 2 when the order of the group is odd. When the order of the group is even. So that gives us another way of sort of thinking about order and how many elements of a given order we might have in a certain group setting. So I do want to talk about the torsion subset example, but unfortunately I'm out of time for today's live stream to do so. So I do want to add some comments. I'll add these into our Slack channel rather than making another video out of them. So for those of you who are my students taking this exam tomorrow, continue to be in conversation with me via the Slack channel as you have additional questions today, as you're looking over this video. If there's anything you want to clarify, please do so that way. And then good luck on the exam tomorrow.